Okay, so the first thing I wanted to cover on the exam is to print out your formula sheet, keep your work organized, and carry 5 decimal places for all intermediate calculations. I went back and kept everything in fraction form. That way, it's not, you don't have to keep dividing with crazy numbers and stuff. It's just easier to keep everything in fractions. For this exam, I will say it's very important to keep your work organized because you will get stuff wrong, and most of these questions build off of one another. So if you get one wrong, then all the answers that come after that will be wrong. So the first thing we're going to start off with is matrix conditioning. So we can find the conditioning number of a matrix by multiplying the matrix A times the inverse. So what does the conditioning number tell us? The conditioning number will tell us if it's well conditioned or ill conditioned, depending on the Ka value. So the Ka value is considered large when it's greater than or equal to 10 to the 7 for single precision and greater than or equal to 10 to the 12 for double precision. So when Ka is large, there's increased uncertainty. So when you're doing your problem, small residuals will not necessarily indicate an accurate solution. So you just remember when we're doing all our problems, we're checking the residuals that they're getting smaller and smaller, which each iteration, right? But when our Ka value is very large, we can't do that because it's not necessarily going to guarantee that we have an accurate solution. Mainly on the exam, though, we're going to be focusing on what small conditioning numbers are. So basically, small conditioning numbers are anything less than 10 to the 7 for single precision and anything less than 10 to the 12 for double. So if Ka is small, then the small residuals do indicate an accurate solution. So that's awesome. And then here I have an example for you on how to find the conditioning number using the L infinity norm. So if most of you guys haven't taken matrices and linear algebra, this might be a struggle for you, which it was for me because I did everything on my calculator when I took this class. So I taught myself this last night. And it was really horrible. But basically, you're going to start by converting your 3 by 3 matrix to a 1 by 3. T186, I think it's T189X or something like that. But most graphing calculators and other calculators can definitely do matrices. Let me see if I can find it. Give me one. All right, sorry. All right, sorry guys. I went to go get the calculator. So this is the calculator I have. It's T136X Pro. It's pretty awesome. You can use it for all your engineering exams, and it does conversions and stuff. It's pretty cool. I like it. Yeah, I'm sorry about the PDF being blurry. I'm not sure why it's doing that. But if anyone has any helpful tips on how to fix that, just let me know.
I think if you change how you're exporting it, there should be like a DPI setting or like a quality setting.
I was just printing it to PDF. I think it might be the scale.
Yeah, do actual size.
Ooh, that turns into 80 pages.
You might be able to go into more settings and change your paper size.
Okay, yeah, that's a good idea. Probably go. All right. Do you guys want me to take my time and do this, and then I'll send you guys an updated version that's hopefully not as blurry? Or
Yes.
okay, just give me one moment. Yeah, if you guys want to send the review to other people, that's totally fine with me.
What program are you using to export this?
I'm just using OneNote, like the print to
Oh,
PDF option. It still looks blurry. All right. If someone has like an actual solution, just let me know. I can share this notebook with you guys, but I don't know. That would be weird. I don't know. All right. So I'm gonna move on for a moment. Maybe someone can take screenshots of. Does it look better on Zoom at least, or no? Open OneNote. Okay. Yeah, that's true. I'll have to open that up later. I don't think I
question.
actually know. Yes.
Under one, the first step where you simplify the matrices down, is the absolute value A, like infinity equals 15, is that the same as the like infinity norm, like L infinity?
Yes. So that's the notation for the infinity norm of matrix A. So
Okay.
as you can see here, in order to simplify the 3 by 3 to 1 by 3, it's pretty simple. You're just basically adding them all together, adding the values. And once you do that, you get 11, 13, and 15. And then you take the infinity norm. So in this case, it would be 15. So then the infinity norm for matrix A is 15. And then for the inverse, it is 0.21.
It's just
So
the
in
highest
our,
value in the vector.
yes.
And then okay, and then for these same vectors, what would be L2? Like if
You
they
do
had
not
asked
have
for
to do L2 at all for this exam.
Okay.
It's just a different formula. I think you have to square it and then square root it.
So like square all of them, add them together, and then take the square, like the distance formula basically.
I think so. I think that's how you find the L2. I have to look at the formula sheet, but you won't have to do this for the exam. It's just
Yes,
gonna
you're
be
right. The
infinite.
L2, you got it right that way. The square and take the square and then yep.
Okay.
Okay,
All
perfect. Thank you.
How did you get 15? I see how you got 11, 13, and then I got lost.
Oh, that's a 9. I'm sorry. That's a
That's
9.
that's supposed to be a 9. The 0.
Yeah. Yeah.
Oh, okay. Okay, cool.
Okay. All right. And then you just multiply the two highest values in those vectors, and it gives you a conditioning number of 3.15. So since the conditioning number is way smaller than the bounds that we discussed earlier, we could say that the matrix is well conditioned and the small residuals will indicate an accurate solution. You're given, yes, you are going to be given your inverse matrix. Yeah, so I changed the Gauss elimination direct methods. I don't know if you could see that. I was doing that late at night, but I did go and update it. I'm trying to figure out the PDF stuff, but I'll show it to you soon. And I changed everything to fractions, so hopefully be easier to understand. All right, so when we're solving a linear system of equations, such as ax equals b, which is pretty much this whole exam, except the last question, pivoting is not required when the coefficient matrix is diagonally dominant. So we pivot when the matrix is not diagonally dominant. And in order to find if the matrix is diagonally dominant, we look at all the values in the diagonal, and we have to make sure that each of the sum of the absolute values of each of the other terms in that row are smaller than the number in the diagonal. So here I did an example. So 6 is greater than absolute value 3 plus absolute value 2. Same with 7 and 9. So this matrix is diagonally dominant, so pivoting is not required. But it's also good to just pivot, at least include partial pivoting when you're doing your routines in Octave. All right, so now for Gauss elimination, this one I think was the most confusing for me to understand because Dr. Kassab never tested us on this when we took it. It was just Gauss, Seidel, and you and Rafson. You guys get lucky and get tested on all three. I thought I was recording this. If it's not being recorded, I'm sorry. I pressed the record button, but all right.
You are, it
so-
says it is.
Okay, cool. All right, so for Gauss elimination, this is going to be a direct method. I think this is probably one of the more tedious methods to do. So here we go. So given this A matrix and this B vector, let's calculate the triangulated matrix and find A22 and B3. So in order to do this, I added a step 0 because first I left everything, I just left the 6 in here, but I figured that kind of makes it a little bit more annoying with fractions. So I decided to change that into a 1. So we're starting off with this A matrix and we wanted to get it into the form that's directly below it. So in order to get to this, we have to divide the first row by 6. So here I have 1 divided by 6, R1 to stand for row 1 equals new row 1. And we have to divide all the terms in that row. So that includes the B vector. Make sure you do that to the B vector. So then we get 1, 1/2, 1/3, and 1/6 as our new values. And then we can start. So the next term we want to do is A21, and we want that to be 0. So since we want that to be 0, how can we get there? Since we made row 1 equal to 1, we can multiply by 5. We can multiply row 1 by 5 and subtract it, and we can get rid of the term in A21 and turn that into a 0. So doing this, I ended up getting, if anyone has any questions, please stop me because I know this can be a little annoying to do. Okay, so I kept everything in fractions as you can see here. So I did 7 minus 5 divided by 2, got 9/2, and then 1 minus 5 divided by 3, and I got -2/3, which I think someone mentioned in the chat. And then 2 minus 5/6, and I got 7/6. Okay, so now that you have all these terms, make sure to update your matrix. So now you have 1, 1/2, 1/3, 1/6, 0, 9/2, -2/3, 7/6. And now we want to make A31 equal to 0. So essentially, we're just going to do the same thing that we did previously. So we're just going to multiply row 1 by -5 and add it to row 3. And doing that, we get rid of the term A31. Then we have 1 minus 5 divided by 2, and we get -3/2. And then you have 9 minus 5/3, and we get 22/3. And then we have 3 minus 5, 6, 6, and we get 13/6. All right, so now that we have that, we're updating again. So this is our new matrix. Make sure to keep updating your B vector. So now this is our final term that we want to turn into a 0. And remember this, you have to do this before you do Gauss elimination. That's why I think it's so tedious. So we're gonna make A3 to equal to 0. How do we do that? So we're gonna add row 3 and 1/3 of row 2 in order to get a new row 3. So we're gonna have plus 1/3 row 2 to get rid of that -3/2 term. And then once we do the math, we get 64, 0, 0, 64 ninths. And for the B, we get 46/18. And then this will be our new upper triangulated matrix. So this is what we got to. And then A22 in this would be 9/2, and B3 would be 46/18. Does anyone have any questions regarding Gauss elimination?
So Milan, question. So pretty much in the exam, we're gonna have like a question just like this, and then they're gonna ask you, oh, find A21, A23, and find B4. The values of those, pretty much?
Yes, they're gonna ask you, they're gonna give you a matrix and they're gonna ask you to triangulate it and find the values A22 and B3 or B2. So you just have to make sure to do this correctly, and you have to make sure you're correctly updating your matrix as you're going along, because you will get the wrong values if you don't do that. And then there's like 2 questions tied to that problem, so you'll probably end up getting both of them wrong. But I think the main point is to make things easier is first just start off by, I'm sorry, my thing just stopped working. Where'd it go? No, we don't give any partial credit in this course, unfortunately. It's all multiple choice. We just ask you to submit your scratch work to make sure that you guys are actually doing the work yourselves instead of just, cheating and stuff like that. But I just had a glitch and everything's like, I'm gonna close this. Okay.
Where can we find this PDF on web courses?
I haven't uploaded it to the announcements or anything. I put it for my class section. If you're not in my class section, just shoot me an email so I can send it to you.
Okay.
All right. So I think we have this working again. I just have to. Okay, so what were we saying? All right, so the first important thing is when you get this matrix that you have to triangulate, the first term, A11, you always want to make that 1, just to make all of the math easier. And if you don't make this 1, you're going to get the wrong answer on the exam. So just make sure to start off by making that first term 1, and then moving down and following the upper triangulated pattern. That is not, should be at the top.
Milan, quick question. So you say the first term from the matrix sake, we had to make it 1, correct?
Yes.
But what about if we, I was trying to do the same exercise. What about if we multiply negative 5/6, and then I could subtract to the equation 2. Can I do that too? And I had this.
What do you mean? Like what do you want to do? You want to multiply row 2
Row
by
1, no,
row
row 1 by negative 5/6.
negative 5/6. So we want to make the first term 1, or like you can do that, but for this, we want to make the first term 1. If you don't make it 1, you will get the wrong answer on the exam. You have to make that term 1 for the exam. There's other ways you can obviously do elementary row operations, but I was talking to one of the TAs because that's what I did, and I ended up getting one of the questions wrong when I was taking the exam myself, and it's because of that. So just make sure you want to start this first term, make it 1, because this is the matrix that I believe Kasab wants you guys to follow for the upper triangulated.
Okay, thank you.
Okay, no problem. All right, so now that you guys make it 1, just keep moving on and have the other terms set to 0.
So only the terms, only the top row you divide by, whatever you divide by 6 to make it 1, or?
Yeah, I divided by 6. I'm sorry that my thing is so glitchy. I'm gonna try to close out of other things maybe. Okay. All right, yes. So I just divided the whole top row by 6 to make it 1. Why are you so glitchy? Maybe it's because 2 of them are open. All right, so once we do that, yeah, so basically we want to do that because I think for this class, it's like established that we want our origin to be 1, so that A11 term should be 1. All right, so let's move on if there are no other questions regarding that for Gauss elimination. So now let's move on to finding the solution vector and the residual. So first, what do you guys want to do first? The residual for the initial, we can call this the initial residual initial. All right, so the formula for the residual is R equals AX minus B absolute value. So I think the first thing I recommend doing, just to make things a little simpler, is write your terms in as a system of equations instead of matrix form. That way you guys can see exactly what you're multiplying. So I rewrote matrix A into its 3 independent equations. So we start off with x1 plus 1/2 x2 plus 1/3 x3 minus 1/6 b1 equals r1. I kind of already put it in the matrix form. And then same with our second equation. So we have 9 divided by 2, x2 minus 2/3 x3 minus 7/6 b2 equals r2. And then 64/9 x3 minus 46/18 b3 equals r3. So how do we find these? Basically, I don't know if I want to do the math right now, but you're just going to plug in your, oh, I guess you can't do the residual before you find the solution. LOL, my bad. Okay, cross that. I messed up. I forgot that this is Gauss elimination. So we need to find our solution first, then you can find your residual. So in order to find our solution, it's pretty simple. You do back substitution to solve. So you're going to start off with row 3. And from row 3, we can tell that 64/9 x3 equals 46 over 18. From there, you're going to solve for x3, and I got 23 over 64. And then what you're going to do is, since you're, I'm sorry, I just got the chat back up. So when I took this class, I did this on a calculator, but you can do it by hand. I'm not sure how much work you guys need to show for your exam. All right, but basically then you're going to solve for x2, and you're going to plug in the value you found for x3. So you get 9/2 x2 minus 2/3 times x3 equals 7/6. And then solve for x2, you get this form, like this form, which I did not simplify. And then you're gonna update, you're gonna write the next system of equations, which is gonna be x1 plus 1/2 x2 plus 1/3 x3 equals 1/6, and you're gonna plug in the values you found for x3 and x2 into this equation in order to find x1. So that's why they call it back substituting, because you're starting from the bottom. You're starting from row 3 to find solution x3, and then row 2 to find solution x2, and then you're going to go all the way up to row 1. So you're going to start from down here and work your way up to find your solutions. All right, so then once you have your solutions, you can put them into the residual form like we talked about before. And then once you have that residual form, just plugging the x values you found into here. So you're just going to plug in, so we have x1, x2, and x3. So just plug in x1, x2, and x3 into all the corresponding spots, and that's going to give you your residual vector. And then the residual infinity norm is just whatever is the highest, the absolute value of the highest value in there. So it's just going to be absolute value of highest value, highest residual, or I should say biggest residual. All right. Is there any questions regarding that? Okay, so just to make sure we got it, x1, x2, x3, then multiply it against the upper triangular matrix and subtract b. Yes. Can I show my work to get the final residual? I have to do the actual solution. Can you quickly summarize the steps? Okay, so the actual steps of this problem. So first, you're gonna get it into upper triangulated form. So I'll write it. Gauss elimination. All right. 1 upper triangular. And then 2 solve for solution vector using back substitution. And then step 3 is find residual vector. Which is just going to be r equals ax minus b. Okay. So that's a basic summary for the Gauss elimination. Let me read what someone else said. Can you show the work to get the final residual? I can if you guys want to do the math with me quicker. Someone can tell me what x2 is and 2 divided by 3 times see. So 2 times. Divided by 9 divided by 2. If any of you guys get these solutions, please just let me know before I do. Plus 23 over 96. Okay, so that is 112. Times 9 divided by 2. So that's just gonna
I posted
equal-
him in the chat.
Oh, you did? Cool, thank you. Okay, so you guys got this. All right, so you got x3 to be -7.
Sorry,
Alright.
that should be X1. That's my bad. Not
Oh,
X3.
X1. Okay. All right. So X1 should be -764s. And what'd you guys get for X2? 5/16?
5/16.
Awesome. So now that we have those values, we can just plug them into the problems over here. So you have X1 equals -764s plus 1/2 times 5/16 plus 1/3 times 23 over 64. And then minus 1/6 times, oh, my bad. This should just be 1/6. These should all be 1/6. Okay, so now that we do this, let's do this. All right, so R1. -764 plus 5 over 32 plus 23. What is that? Is that a 3? 64. 192. 333. That's gonna be. That's gonna be. Do 192 for everything. 21. Plus 30 plus 23, which is going to equal 32 over 192 for R1 and R2 R2 is going to be 5/16 and 23/16. I forgot to subtract the 1/6. Okay, let's see. Minus 1/6. So that's going to be 32, 192. So that's going to give us 0. And that's what we expect because we want these residuals to be really small. So since we didn't do rounding, our residuals are probably going to be pretty small because it's going to be pretty accurate. But if we would have rounded, we would have had more decimal places in here since we didn't have any rounding. All right, now for this one, we have, so I'll round for this one. I'll just do the math in here and so you guys can kind of see.
So since we did it like analytically, our residual should be 0, but if we had it in a computer, it should be some sort of number.
Yeah, so like I'm gonna do it by hand now with the calculator to kind of show like the rounding. So I did this in the calculator and I got 0.479 for the second one. Let's see. Minus, oh wait, no. LOL, I got 0 again. Oh my gosh. Yeah, this is what happens when you use a lot of fractions. On your exam though, I will say that if you don't use fractions, if you would just want to use decimal places, I think either way you're going to get the right answer because it's going to ask you for the highest value of the residual norm. And since we kept very accurate representation of all the numbers, let's see, times, that's going to be 23 divided by 9. Yeah, these are all super accurate. They're all going to be 0. Yeah, so these are all 0. So your highest one would be 0, which is like the same as it would be on the exam. For I saw it, it's a very small value. So if you don't keep your fractions and you use decimal places, you could use decimal places in order to get an actual residual vector if you guys wanted, but I think they're still debating on whether the answer should be 0.00 or like a scientific number. They're like debating if it should be like 7.5 times 10 to like the negative something, which are both really, really small values. So if you don't see 0.00 on your exam, use decimals and just instead of using fractions because you're going to get 0 if you use fractions.
So for the exam, are they counting on us calculating these with truncated to 5 decimal places then?
Yeah, I'm gonna say they probably are because that's in the directions and I shouldn't have done fractions. Yeah, just use the 5 decimal places and you'll get the right answer. Good point. All right. So the next thing we're gonna wait, does anyone have any other questions regarding that problem? No. Okay. So just know whoever said make sure to keep the 5 decimal places. That way you guys can get the accurate solution and you guys should expect it to be really, really full. This is a direct method since it's Gauss elimination. It's not an iterative method like Gauss-Seidel or Jacobi. But what was I going to say? I didn't. Okay. Shoot, I forgot what I was gonna say. All right, so let's just move on. So the next thing is gonna be floating point operations. So this is pretty easy. So the floating point operations include adding, subtracting, multiplying, and dividing. And it's all the operations that take place in order to solve the problem. So the number of floating point operations can be found in direct methods such as Gauss elimination using n cubed. So n is going to be the number of equations you have in a given system. So in a 2x2 matrix, we know that there are two systems of equations, and I wrote them out here for you in their expanded form. So we have 1x1 plus 4x2 equals 10, and 3x1 plus 5x2 equals 7. So since we have two systems of equations, our n is going to equal 2. So you just do 2 cubed and you get 8. So if we had a 3x3 matrix, yeah, so errors from truncation for Gauss elimination. You have to remember that these are direct methods, so that's where the error is going to accumulate if there is any, because if you use the fractions, it should be exact. All right. What was I going to say? You will not have to do LU substitution, but I do have a question. If I gave you guys a 3x3 matrix, how many floating point operations would it take to solve? $27. Yep. Not 9. 27, because it's 3 cubed. Awesome. All right. So next, let's go over the determinant. So before starting Gauss elimination, it is important to check the determinant. So why do we want to check the determinant? If our determinant is equal to 0, we cannot solve the problem. So that's why you check it. It's always good protocol to just check it before you start. All right, so how do we find the determinant of a triangulated matrix? So in order to find the determinant of a triangulated matrix, it's actually really simple. You're just going to multiply all the terms in the diagonal. So you're just multiplying A11, A22, and A33. So for this example, it is 687, not 587. So let me make sure that's the same. 336. What was that doing? Okay, so the determinant in this example problem is equal to 336. So since the determinant does not equal 0, we know that the problem can be solved. But how do we find the determinant of an untriangulated matrix in order to check it? So I did different colors to kind of explain this. Basically, we're going to start off. The trick is for a 3x3 matrix, it goes positive on your first column, negative on your second column, and then positive on the last. So what are we going to do? We start off with 1, and then we're going to multiply by the little matrix that is formed here. So we're choosing this 1, and then we're going to exclude all the other numbers that are in the row and column. So then we're just forming this new little matrix, which is going to be composed of -1, 0, 4, and 6. And then for our next term, 2, we have minus, because that's the rule, -2. And then we're going to form a new little determinant, but with all the numbers not in the row or column. So we're using 0, 2, and 0, 6. And then for our last term, 3, we're excluding all the values in its row and column, and we have 0, -1, 2, and 4. So from this point, once you have this set up to find your determinant of C, you are going to cross multiply. So in when you cross multiply, I have a little example here. You have A times D, and you're going to do A times D minus B times C. So I have determinant C equals 1 times negative 0 minus 0 minus 2, 0 minus 0 plus 3, 0 minus negative 2. Be careful. Don't forget your negatives because I know I always do. Okay, so when we simplify this, we get negative 6 minus 0 plus 6, and that's equal to 0. So this problem cannot be solved because the determinant of A is equal to 0. So you guys are definitely going to have to do that on your exam. So make sure you feel comfortable finding the determinant of a matrix that is not triangulated. Okay. Sorry, I don't have the chat on in my.
Hey, Milan, question.
Mhm.
If we do the determinant and we don't got 0, we got like 1 or 2, so that means that matrix has a possible solution, right?
Yes. And yes, this is all right. So let's go on. All right. So when are we guaranteed convergence when we're doing these problems? So when we're using iterative methods such as Gauss-Seidel and Jacobi, we can guarantee convergence when the matrix is diagonally dominant and the eigenvalues are all less than 1. So we already went over how to find out if a matrix is diagonally dominant, but what do you guys know about eigenvalues? So the reason that we want to find eigenvalues that are all less than 1 is because when we pre-multiply the theoretical T matrix by the error vector, we want to shrink it in order to guarantee convergence all the time. So we have to look at the eigenvalues. If the eigenvalues of that matrix are all less than 1, then convergence is guaranteed. So I have an example eigenvalue set here. So let's say you are given any theoretical matrix. Doesn't really matter at this point. We're just looking at the eigenvalues. All the eigenvalues in this vector are all less than 1. Since all of these are less than 1, convergence is automatically guaranteed. Because no matter what's happening, no matter what the theoretical matrix is, since the eigenvalues are all less than 1, anytime it pre-multiplies the error vector is always going to get smaller and smaller, and it's going to approach that 0. Are there any questions regarding that?
In this
So-
case,
Go ahead.
in this case, would the eigenvalues be given to you, or are you calculating them?
So you guys got lucky. You guys are not calculating them this semester. You will just be given them. So do not worry about calculating them. All right. Any other questions? You're just pretty much, you're not necessarily going to have to find the eigenvectors. You're going to be given the eigenvalues, and you're just going to be asked conceptual questions regarding the data that you have. All right. So now let's go on to Gauss-Seidel. It's, I think, a much chiller method than Gauss elimination. So let's start off by finding the initial residual vector. So we have our A matrix. Yes, so eigenvalues is going to be conceptual. There's not a lot of conceptuals on this exam. I think that's why it took me so long to make the review for it. It's mostly just math and being able to interpret the results from that math. Yeah, no problem. All right, so we're finding the initial residual vector given this A matrix, this B vector, and an initial guess of 1, 1, 1. So I think the first thing to note is just anytime you see your initial guess, set that equal to x1, x2, and x3. That way you guys know when you're writing these equations down, you know what your x1, x2, and x3 is, and there's no confusion, because I know a lot of people, when they're doing these problems, it's a lot of math and you can get confused if you're not careful. So the formula stays the same for the residual. We have R equals absolute value AX minus B. So I have R1 equals 6 times X1 plus 3X2 plus 2X3 minus B1. So that's going to give us 6 times 1, that's going to give us 10. And then R2, it's just the same thing. We're just plugging in ones for all our X values since that's our initial guess. And we get 11. And then for R3, we get 12. So then, therefore, that gives us the residual vector to be 10, 11, and 12. And our residual infinity norm is going to be equal to 12. So that is our initial residual infinity norm. Will we be given the initial guesses? Yes, you guys will be given the initial guesses. All right, so that was pretty simple. Now we're going to go to finding the solution vector after one iteration using Gauss-Seidel. So what is the main difference between Gauss-Seidel and Jacobi? So in Gauss-Seidel, we are constantly going to be updating our x1, our x terms. So as you can see here, I would write down these formulas that I have here. They're like already in a good form. I'll just write them down for Gauss-Seidel. This is pretty much all you need to know. Once you have the formula, you can just put in your values. So this is saying that in order to find the next iteration of x1, we're doing x1 equals b1 minus a12 times x1 and x1n, so that, or x2n, I'm sorry, x2n. This is going to be our initial guess, and this is our initial guess. And then we're dividing by a11. So the first term we're getting is 1 minus 3 times 1 minus 2 times 1 divided by 6, which is equal to negative 2/3. So it's important to note, because you guys are going to have to do Gauss-Seidel and Jacobi, is the Gauss-Seidel and Jacobi term is going to, for the first term, is going to be the same. But then it's going to change. So in Gauss-Seidel, the main difference is we're going to constantly be updating that value. So now that we have x1, we're going to plug in our x1 value into the new equation. So in order to find x2, we have x2 equals b2 minus a21 times our new x1. That's what n plus 1 means. So, and then we have minus a23 times xn, which is still our initial guess, all divided by a22. So there we get 2 minus 5 times negative 2/3 minus 1.1, no, 1 times 1 divided by 7. And you end up getting 1 divided by 21. So now that you have this value, you're going to update your solution to incorporate your new x2. So here we have, in order to find x3, we have B3 minus A31 times X1, your new X1 minus A32 times your new X2 divided by A33. And we get 3 minus 5 times negative 2 over 3 minus 1 times 1 over 21 divided by 9. And when you simplify this, you end up getting, oh my gosh, 132 over 189. So that means our solution vector is going to be negative 2/3, 121, and 132 over 189. So now that you have your first solution vector, they'll probably like ask you, oh, what's x2? And this after one iteration. So that'd be your x2, this is your x1, this is your x3. Now, how do we do a second iteration? It's simple. It's the same process. You're going to be using the same formula as before, but the only thing that's going to change is your initial guess. Your initial guess now is going to be the solution vector we just found. So you're going to plug that in for all your, everywhere you see xn. So that's going to end up looking like 1 minus, it's the same formula as before, but we have 1 minus 3 times 1 over 21, because that's our x2, our new x2. And this is going to be our x3n, and we have negative 2 times 132 over 189, and you end up getting negative 17 over 189. And then you just have to remember to keep updating. So now we have our 2 minus, and this is going to be our x1n plus 1 term, and this is just going to be x3n, which is going to be our previous guess. And we have, once you do the math, you end up getting 331 over 1,323. And now you do your last update, and you, so that means this is x1n plus 1, this is x2n plus 1. So just make sure to update, and once you simplify, you end up getting your solution for x3 to be 1411 over 3969. So that's how we find our second iteration. Okay. Sorry guys. There's a lot of things, so just, yeah, don't use fractions. I just did it to simplify the math a bit because I find it a little bit difficult to have like nice work when there's a million decimal places everywhere. So yes, Jacobi does not update. Yeah, where did we get the initial values we input? So the very initial values were given within the problem statement itself up here where we first started the problem. So the initial guess in the beginning was 111. Then once we ran through our Gauss-Seidel, our first iteration gave us this new solution vector, which is going to be our initial guess for our second iteration. Yes, so the very first is 111. I think the numbers you're going to be getting on the exam are going to be a little bit nicer. I think mine were just really disgusting because I made them up and sometimes they turn into really gross decimal places. It's 25 questions and there are no multiple answers. All right. So we just finished our Gauss-Seidel. Now we're going to go on to our Jacobi. Our Jacobi is a lot simpler. It's just going to be essentially the same thing, but without the updates. So our actual formula for our x1, our new x1 is going to be the same as our Gauss-Seidel. So that term is going to stay the same, just do the same process. Now, what changes is our x2 term. So our new x2 term, we're still going to be using those initial guesses. We are not updating. So we're going to have B2 minus A21. This is going to be our initial guess and initial guess. Minus A23 X3N divided by A22. So when you do the math, you end up getting -4/7 for our X2, our new X2 solution. And then for X3, we're still not updating. These are still going to be your initial guesses. So I think that's why it's a lot simpler. So you just, since it's all one for the thing, it's just going to be pretty simple. So you end up getting 3 minus 5 minus 1 divided by 9, and you get -1/3. So the solution vector becomes this. And then from here, we can find the residual vector. So don't mind my math, it's just discussing all over the place. It's just essentially the same thing to find the residual vector. So we write down our equations, we break down our matrix into the systems of equations, and we do A times X minus B. So we have 6x1 plus 3x2 plus 2x3 minus b1 is going to equal all this nonsense. And basically, we're just inputting our x1, our x2, and x3. So we don't have to go through that because that's just plugging and chugging once you actually have these equations written down. And your final solution will end up looking like this. And then we are looking for the residual infinity norm. So the residual infinity norm is the absolute value of the highest magnitude value, whatever, in the vector, which ended up being 208/21. All right. Yeah, guys, just take it step by step because the math does get a little confusing because I know it's a lot of methods all at once. Just I feel like make a formula sheet for yourself, not necessarily use it on the exam, or you guys are allowed to use the formula sheet. You guys are asked to print it out. Honestly, I would just write down the steps on how to do each one on there because I know that formula sheet is basically crap when you look at it if you don't know how to read it. All right. So the next thing I want to go over is iterative methods and floating point operations. So in order to find the number of floating point operations, which we already discussed, which is adding, subtracting, multiplying, and dividing, needed to reach convergence in an iterative method such as Gauss-Seidel or Jacobi, we can use the formula k times n squared. So keep in mind, this is different than the formula we were given for floating point operations in our direct methods, which was just n cubed. For this one, it's kn squared, so you will be given a k value. So that's a little hint in case you were super lost. So here I have an example for you. So if it took k equals 7 Jacobi iterations to drive the residual norm below the tolerance set by the user, what is the number of floating point operations? So we're just doing k times n squared, and you get 7 times 3 squared, which equals 63. All right. And then we have our nonlinear Newton-Raphson. Oh my gosh. All right. So I think this one can be a lot of confusing for a lot of people. And the reason this one I feel like is most confusing is because there's a lot of steps. So I think the best way to break this up is when you're doing your nonlinear Newton-Raphson, first thing, find the residual. Second, find the Jacobian matrix and the inverse Jacobian matrix. Third, find your solution. Sorry guys, what's going on? Is something happening in the chat? I can't see. All right. So the first thing we're going to be doing is we're given these two equations. So they're going to be simple like this. You're going to be given f1 xy equals 3x minus 2y squared, and f2 xy equals 4x squared minus y. So you guys don't have to worry about not being able to take those partial derivatives in case you forgot how to derive, because I know some of us, it's been a while, but these are pretty simple. So I think you'll pick it up if you don't remember. So we're giving these functions and we're given an initial guess of what x equals 1, 1. So as you can see here, I just like to write our initial guess, which is going to be equal to our x and y values. So the residual, in order to find the residual for the nonlinear Newton-Raphson, it's going to be a little different. So the residual is equal to the function evaluated at the initial guess. So, or evaluated at your xn. Right now, it's going to be our initial guess. So our residual is going to equal 3, and then we're plugging in our initial guess, which is 1. So 3 times 1 minus 2 times 1 squared, which is equal to 1. And then we have our f2 xn equals 4 times 1 squared minus 1 equals 3. So I wrote it this way because it'll be easier to understand if you are looking at the formula sheet that Dr. Kassab posted. You'll already know that this is like one of the parts in order to find our nonlinear Newton-Raphson. So then given this, we found the residual vector to be 1 and 3, which is equal to f1xn and f2xn. So once you do that, you're going to move on to your second step, which is finding the Jacobian. So how do we find the Jacobian? We do this to linearize our coefficient matrix. So, or create a linear coefficient matrix. And how do we do that? By taking partial derivatives. So we want to take partial of df1 with respect to dx, df1 with respect to dy, df2 with respect to x, and df2 with respect to y. So let's see if I can bring up the functions. So the derivative with respect to x of the first function is just going to be 3, and the derivative with respect to y of the first function is going to be negative 4y. And then the derivative of function 2 with respect to x is 8x, and the derivative of function 2 with respect to y is just negative 1. Now, once you have this, you will probably be asked, what is J22 in this? Does anyone know? In the Jacobian matrix, yes. So they're going to ask, yeah, it's definitely negative 1. So this is our J22 value. So in our initial Jacobian matrix, this is going to be what it looks like, and our J22 is equal to negative 1. And just keep in mind, these two are going to be constants no matter what. If you take a look, because they're not being multiplied by an x or a y. So now we want to find the inverse of the Jacobian. How fun. So how do we find the inverse of the Jacobian? So the formula for that is 1 over the determinant of m times, as you can see here. So we start off with the matrix M, which is equal to A, B, C, D. And as you can see, you're going to multiply by 1 over the determinant of M times this new matrix. So what happens is when you're taking the inverse, C and B become negative and D and A switch places. So I can write that somewhere, like these switch. And then C and B become negative. I don't know how to write that, but you guys can kind of see there. And then just remember, finding the determinant is just AD minus BC. So in order to find the inverse Jacobian, we are plugging in our values. So here we have 1 divided by 3 times -1. Oh no, I'm sorry, I didn't actually do, wait, yeah. 3 times -1 of our original Jacobian matrix minus 8x times -4y times, and this is where we have our new Jacobian matrix already emerging, -1, 4y, -8x, and 3. So this ends up giving you the inverse Jacobian with the form of 1/3 plus 32xy, and it's being multiplied by the matrix -1, 4y, -8x, 3. So once we have the form, like the formula for the inverse Jacobian, we can just have that off to one place because that is going to constantly be updated in response to whichever initial guess you're putting in. So with the initial guess that we were given, which was 1, 1, I think. Let me double check, I don't remember. Yes, our initial guess is 1, 1 for here. So given the initial guess of 1, 1, we are going to find the initial Jacobian matrix. So we're just plugging in. So let me write that down. So our xn is going to be equal to 1, 1, and we're going to plug in these values for x and y. So we're going to get 1/3 plus 32 times 1, 1 time, which ends up being 1/35. And then we're going to plug 1 into our matrix, and you end up getting -1, 4, -8, and 3. And then we're going to multiply by our determinant, and we end up getting -1/35, 4/35, -8/35, and 3/35. So now that you have this, you have almost everything you need in order to incorporate your one-step Newton-Raphson. So step 3 is now finding the solution vector using the one-step Newton-Raphson. So this is the one-step Newton-Raphson. So you can see here that your new solution is going to be equal to your initial guess minus the inverse Jacobian matrix evaluated at your initial guess times your function evaluated at your initial guess. So this is really the residual. So we already found that. We already found this, and now we are just going to be plugging in our values. So we got xn plus 1 equals 1, 1 minus our inverse Jacobian matrix multiplied by our residual vector. So first thing we're going to do is we're going to rewrite our 2 by 2 matrix into a system of equations. So I just do this I already explained it, so I can visualize it better. I ended up getting -1/35 x plus 4/35y is going to equal inverse Jacobian times f1xn, blah, blah, blah. And then we have -8/35x plus 3/35y is going to equal our negative Jacobian times our residual vector 2. So now that we have that, we're going to plug in our residual vector values for x and y. So sorry for my notation, it got a little ugly. I didn't know what to call this. We have -1/35 plus 4/35 times 3. And that is the values from, so let me we're multiplying by 1, and we're multiplying by 3. That's what we're going to multiply by. And we end up getting 11 over 35. And for this one, we are multiplying by 1. And we're multiplying by 3. And you end up getting 1 over 35. And then you plug in, and you get these values, which end up being 24 over 35. So now, okay, so now that you have it in this form, you can just subtract, because now you have what this guy equals. So you have xn plus 1 equals 1 minus 1135 over 135. And then I ended up getting 24 over 35 and 34 over 35 for my first solution, or first iteration. Now we can use this to find the iterative of convergence. Keep in mind though, yours is going to look a little different because I didn't round in mine, so mine's a little bit more exact. That's why I got like the exact values I had before. So your iterative of convergence is just the absolute value of your first iteration minus your new iteration minus your previous one, which just ends up being 24 over 35 and 34 over 35 minus 35 over 35 and 35 over 35, which is just 1. I just multiplied by 35, and you ended up getting negative 11 over 35 and negative 1 over 35. And you take the absolute value, and then therefore the infinity norm of the convergence of the iterative convergence is equal to 11 over 35. And then we have our second iteration. Yes. So when they say after one iteration, that is equal to I equals 1. Because remember, and then once you're, so I feel like it kind of depends when the way you're noting it. For me, when it says your first iteration, you have your like xn is your initial, and then your xn plus 1 is your first iteration. And like, I'm not gonna lie, sometimes I write it like that, but I feel like that's not proper notation. So like, I didn't want to like impose that on anyone because I'm not sure if that's the proper notation for it. But in my head, that's kind of how I think of it. Let's see. Yes, you can see the residual vector equation again. It's just your function evaluated at your initial guesses, which is all the way up here. There's another residual one where you plug the values in that one where I plug the values in. Oh, this big thing, the solution, the one-step Newton-Raphson, or oh, okay. Yes, I can show you the inverse Jacobian equation. All right, I'm gonna move up now, and the inverse Jacobian equation is right here. This is how you find the inverse. A little example. We apply it. And then after you guys are done looking at this, we'll go over what you need to update in order to find the second iteration. Yes. All right. So the first thing you want to do when you're starting off your nonlinear Newton-Raphson is I like to start off with the simplest step first, which is finding our initial residual. So our initial residual is going to be equal to the term fxn. And if you look at the formula for your Newton-Raphson, your one-step Newton-Raphson, it's going to equal so essentially why I like starting off with the initial residual is because our residual is equal to fxn. So there we're just going to start off by finding the simplest term. So we have we're just going to do our actual equations that we were given. We're just plugging in our initial guesses and we end up getting 3 times 1 minus 2 times 1 squared, which is equal to 1. And then we're going to plug in our initial guesses into our second equation, which gives us 3. So now that we know this, we know what f1 xn is and f2 xn is. So now we can kind of write, we have this after this step. Or I can put the actual values in there to maybe make it easier. So now we have these two values here. And then we go on to find the Jacobian. So in order to find the Jacobian, we have to take our partial derivatives with respect to x and y of both functions, and you end up getting -3, -4y, 8, and -1. Now, the next step from here, once you have your Jacobian matrix set up, is you want to take the inverse of the Jacobian. So in order to take the inverse of the Jacobian, the formula is 1 over your original determinant, the determinant of the original Jacobian matrix times D, -B, -C, and A. So keep in mind, D and A are switching and B and C are both becoming negative. So that's essentially what you have to, the manipulation you have to do to the terms inside of the matrix. So from there, we find the determinant of the original Jacobian matrix. So we can say that the step after finding the Jacobian is find determinant of Jacobian. So the determinant is equal to determinant of Jacobian is equal to 3 times -1 minus -4y times 8x. So determinant of the Jacobian equals -3 plus 32xy. So we can say that this is like the step that you should do immediately after finding your Jacobian matrix. Now that we have the determinant, we can just plug that into our formula and we can switch our rows and make C and B negative. So now we're computing the inverse Jacobian. We have 1 over the determinant of our original Jacobian times our new matrix. So now that we have this is what you're going to be updating with each iteration, because this is where you're going to be plugging in your your new initial guess. So like every time you get your xn plus 1, xn plus 2, and so on, this is what's going to constantly be changing along with your residual. We'll discuss that after we're done going through this. So you want to, wherever you have it on your paper, make sure you can see this formula clearly, because you're going to probably want to reference back to that a lot when you're doing this problem. So now that we have that, we're going to find our initial Jacobian matrix by just plugging in our initial guesses, which were 1 and 1. So we plug in 1 for x and we plug in 1 for y, and we end up getting this over here, negative 1 over 35, 4 over 35, negative 8 over 35, and 3 over 35. So now that we have this, we pretty much have almost the complete form of the one-step Newton-Raphson. So let me just, okay, so we have minus, let's see, four over 35, 3 over 35 times 1 over 3. Okay, so this is what we have so far. So now, before we incorporate our nonlinear Newton-Raphson, I guess you can say we should find what our Jacobian xn times, or xn times our fxn is equal to. So in order to do that, I rewrote my equations as the matrix as a systems of equations, and I plugged in the x and y corresponding to the residual vector. So when you plug in those values, you end up getting 11 over 35 and 1 over 35. And then you can essentially do your one-step Newton-Raphson. So you have your initial guess, which was 1, 1, minus 11 over 35 and 1 over 35. And you end up with the solution 24 over 35 and 34 over 35. If you guys have a calculator though, I will say it's a lot easier just doing it in the calculator. It's literally just like, you don't have to do all this math by hand. But I know not everyone has a calculator, and who knows if you guys can go out and buy it right now. But if you were doing it in the calculator, let me see if I can turn on my camera. Okay, so you have second matrix, you put in your matrices, so you can put in A, B, C, and then you can do literally inverse it. So like just like that, just like A to the -1 automatically inverses it, and you get all your values, so you don't have to do all this math by hand. Let's see. All right. So does anyone have any other questions? All right. So now for our second iteration for our nonlinear Newton-Raphson, what are we going to be doing? So now that we have our new solution, we are going to update that with where our initial guess was previously. So we have to update our xn, we have to update our Jacobian, and we have to update our residual. So every time you run through this problem, those are the three main things that are going to be changing, and you're going to have to recalculate for each new iteration, or else you will get the problem wrong. And then it's just like the same simple process, but then it's the end. That's the end of the exam. So it's not too bad, hopefully. Does anyone have any questions or concerns? All right, no problem, guys. Good luck on the exam.
Yeah, will you
Yeah.
be sending, okay.
Yeah, I will. I think someone messaged me saying that they could help me.